Okay, this is going to be shear, example 5. So in example 4 we did talk about this concept of shear flow. Now when we deal with thin walled sections, let's have an example of one. So if we assume that the section was very, very thin, in contrast to, let's just say, a thicker walled section, now we know that in a thin walled section the shear stresses on the outsides must be 0, and obviously that applies to the thicker wall case as well. But the difference between the thin walled and the thick walled is that with the thin walled we're making the assumption that there can be no transverse shear with the thin walled, whereas with the thick walled, even though it's going to 0, there is a shear. So for those flanges, even though it's 0 at the ends, it assumes that it can take a transverse shear force, whereas with the thin walled, because it's so thin, it's convenient to make the assumption of no transverse shear, which is perfectly reasonable. Now if we have a beam, so let's just call it again a simply supported beam with a 20 kilonewton load in the center, which will then allow me to conveniently say that's 10 kilonewtons and that's 10 kilonewtons for the reaction, so that I can use my 10 kilonewtons as the shear force. So up here, before our cut, we've got 10 kilonewtons, and there must be a shear force of 10 kilonewtons, and then after the cut, let's just, for argument's sake, include the 20 kilonewtons there, and for argument's sake include the 10 kilonewtons there. There would be a reactive 10 kilonewton, so that the two would obviously cancel each other out. So let's now have a look at this in 3 dimensions. So let's focus on what's going to happen after the cut. So after the cut, with our thin walled section, so we'll assume that it's thin walled. So just for argument's sake, I might just start the x-axis going along from there. So the x-axis is after the cut. So we've got our beam after the cut, and then we've got our shear stresses being developed along down here. Now let's take out the plates. So we'll have a plate, and this time I just won't show any thickness to the plate. So up there is going to be the web, and I'm just going to show there is a, a vertical shear force of 10 kilonewtons upwards, and then that must mean through complementary shear stresses that we would get that arrangement on the web. Now if I took out the flange, so one flange, let's see if I can do this right, there would need to be a reactive, so that's acting in that direction, so this one here needs to act in the opposite direction, which therefore means that there's going to be, sorry, I think it's going to be the other way. So by complementary shear stresses, it's going to be like that. Let's draw the other one. So that again is reacting against the force on the web. So that again needs to be going along that face there, which tells us that direction is there. Now as for the bottom ones, let's draw the bottom one, and then we draw that down there. We also know that there's going to be a reactive shear, which is going to be like that, so there's going to be a shear force in that direction there, and then for the final bit we draw that bit there, and that one needs to be going there because that is reacting against that one there. So for the top one we've got there, so that must be reacted by that and by that, and then for the bottom one we've got that, which must be reacted by that one and that one, and so from there we can deduce the direction of the shear stresses, and of course assuming that there's going to be no shear stresses transverse, so everything is across. So so we can draw some arrows, so we know the direction of the arrows from that exercise, and then we know that these arrows are going in this direction here, and that one is on that side and that is on that side. And that is what's called shear flow, and we can see that that whole transverse one must be 10 kilonewtons, coming up from 10 kilonewtons there. So on the basis that, let's just draw out the section again, on the basis that the shear stress here must be 0, and also here must be 0 at the end because there's nothing to react against. If we wanted to draw our shear stress distribution for the web would look something like that, as we know, with the maximum value occurring at the neutral axis. And then we would, just by convention, we would draw our shear stresses going like there. So let's just draw a solid line for the center, and then we would draw another one like there. So you might say, hey, that shear stress and that shear stress are in opposite directions, so shouldn't we really be drawing it like that? And yes, we could do it like that, but convention just says, to make our life easier, just make them go round, so that's flipping that round along the horizontal axis. So, or you could think about it just in terms of showing the modulus, the absolute value, so then it doesn't matter whether it's positive or negative. So, having sort of deduced the directions of the flow, so So I'll put some arrows. So obviously it's going to be peak in the center, and then it's going to be decreasing towards the bottom, and then there would be a flow which would reduce in size. So try and make the arrows indicative of the fact that it's going up to 0 at the end, and then these getting gradually longer until the center, and then gradually. So these tractions, so remember that as stress or shear stress is in newtons per millimeter squared. So if you multiply the shear stress by the cross-sectional thickness and also by the length, the sum should be 10 kilonewtons for the sum should be 10 kilonewtons for the web. But we're showing these as tractions, which act along the surface. So that's eliminating the need for the thickness to be taken into account. So in the next continuation we'll be calculating these values.